Hi everyone, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to use this video to explain how you can get the orbital velocity of a smaller object orbiting a larger object when it's on an elliptical orbit, and this is known as the Vis Viva equation. So we're going to derive that, and then you'll have your equation and how you can find that orbital velocity when it's not on a perfectly circular orbit. So for perfectly circular orbits, the orbital velocity remains the same magnitude all the way around. The semi-major axis, which is A here, doesn't change. So it's on a perfectly circular orbit, it's always orbiting with the same speed. That's quite straightforward to calculate because you know it's always going to be going the same speed at any point on its orbit. However, the vast majority of orbits are not perfectly circular, especially in the real world. They are slightly elliptical or very elliptical, and the orbital velocity changes depending on where it is on that particular part of its orbit. So for example, it's when it's closest, so if you see like the green kind of segment there with the planet orbiting the star, it will orbit faster there when it's closer than it does further out. This is one of Kepler's laws for planetary motion. They always sweep out the same internal area as they go around. So when it's closer, it has to sweep out the same area than it does further away, so it has to travel further in the same amount of time, so we get a faster orbital velocity than we do further away. So it's not quite so straightforward to find that orbital velocity when it's elliptical. So some things we need to kind of make a note of before we get started on this, and this is the semi-minor axis and the semi-major axis. Now the one we're really interested in here is the semi-major. So if you take an ellipse and you go along the longest axis, that's the major axis, half of that is then your semi-major axis, and we call that A when we're kind of talking about orbits. So when you see A, that's our semi-major axis. That doesn't actually change. If you've got an elliptical orbit and the object's going around on its orbit and the orbit itself doesn't evolve or change, then that semi-major axis will always remain the same value. However, the distance between the two objects, which we're going to call R here, does change. So as it's, let's say it's a planet, it's going around a star, that distance R is going to change depending on where it is. The semi-major axis is not, it's a constant of that particular orbit. So we're going to need R actually to calculate our orbital velocities. So this is the Vis Viva equation, and if we know the instantaneous distance, so some distance between the two objects at some time, that's going to be R. And if we also know the semi-major axis, which is A, we can calculate the orbital velocity. Now mu here in front of the brackets inside the square root, that is the gravitational constant times the mass. So it's gm basically. So if you come across that, that's what it is. So again, we're going to define some more properties of an elliptical orbit. Now the apocenter, the RA here, is the furthest distance the two objects will have when one of them's on an elliptical orbit. So we call it the apocenter. Has a few different names actually. And on the other side, you've got the closest distance between the two, which is your pericenter, and we'll give that a label of RP. So RA apocenter, RP pericenter. So what we're going to do is we're going to start with the specific orbital energy, and in here we've got the velocity at the apocenter and the distance, the apocenter distance. We've then got the pericenter velocity and corresponding distance as well. Obviously you've got your gm there, which would be your mu, and the specific orbital energy is a constant of that particular orbit. So again, that should remain the same value, and we can put it in terms of the apocenter or the pericenter. So we've got kind of two versions there basically. So what we can do with this here is we can rearrange so that we have the velocities on the left hand side, and then we've got like the distances and the masses on the other side. So we've rearranged that to get it in this sort of form here. Then what we need to basically define again now is the eccentricity. So this is the amount of deviation of an orbit from a perfect circle. So if it's a perfect circle, like maybe on the left you see there, that would have an eccentricity of about 0. Well, we're not about, it would be 0 if it was perfectly circular. And then as it gets more elliptical, it's going to tend towards 1. If it's beyond 1, it's not necessarily going to be a bound orbit at that point. So it's generally between 0 and 1. It's a dimensionless parameter. So it just tells us how elliptical it is, basically. So that's eccentricity, and we would normally define that as E. So we can calculate that from the apocenter and pericenter distances, given like this here. There are a few other ways we can do it. So we can actually use the eccentricity vector as well. So we can use the vectors depending on where, you know, that second smaller particle is. But this way is fairly straightforward. So you can see actually if it's a perfectly circular orbit, then we're going to end up with 0. And as those two distances get bigger and bigger, or the difference between them gets bigger and bigger, we're going to start approaching 1 essentially. So that's how we calculate that. Now, the maximum velocity is going to be at the pericenter. So when the two objects are closest on their orbit, that is the maximum velocity, and that's the equation you can use to calculate that. So again, you've got mu in there, you've got the eccentricity, and you've got the semi-major axis. And you can see that actually as your eccentricity increases, we're going to expect a bigger difference here than we would do, you know, from the other side, which is going to be our minimum velocity. So this time round, this is the apocenter. This is going to give us our minimum velocity. It's the furthest away. So again, think about, you know, one of Kepler's laws. We're sweeping out the internal part of the orbit. So the further away it is, it's going to sweep out more as a function of time, so it will slow down on its orbit. So we've got the two velocities there, and at those two locations as well, if we put that in terms of vectors, they will always be perpendicular to the distance between the two objects, so the pericenter and the apocenter. It'll always be perpendicular at those points, which is similar to what it would be on a circular orbit. So now we're going to consider, or take into consideration, the fact that there's conservation of angular momentum. And if we then look at the specific angular momentum, that's constant, which is given by h here. So we can either put it in terms of the apocenter or the pericenter. So what that basically means is when it's closer, we're going to have a shorter distance, and we're going to have a larger velocity. But when we're on the opposite side, we'll get the opposite. So we have kind of a longer distance and a smaller velocity. So it should always give us the same value. That specific angular momentum is a constant, and it's also conserved as well. So we can basically, if we look at that, we can essentially write that in terms of the velocity at the pericenter. So down there you've got the pericenter velocity in terms of the ratio between the apocenter distance and the pericenter distance times the apocenter velocity. So we've got that now. So what that allows us to basically do is, if we combine that back into what we had a few minutes ago, basically, we can get rid of one of those velocities. So if we put that in terms of the velocity at the pericenter, then we can kind of rewrite that in that manner instead. So we should end up with something like this at the top, but it's actually a little bit more convenient to write it as we do down in the bottom in the brackets like that. So it's basically the pericenter distance squared minus the apocenter distance squared over the pericenter distance squared. So it's just more convenient to kind of write it like that there. So now we don't have the pericenter velocity, but we do have both of those distances and the velocity at the apocenter. Now we can bring the GM out of the brackets now because it's on both parts. So if we bring it out, then we end up with what we have on the bottom there instead. So we kind of, again, we're kind of tidying this up, trying to simplify it a little bit so we can end up with our Vis Viva equation. Now if we simplify that even further, so from the top to the bottom, we can just put it like that there really, because there's quite a few things that we can just tidy up there, and if we put it like that, it makes it a little bit simpler really. We don't need to have it as it is in the top form. So if we go back to the geometry then of an ellipse, that major axis, the full length of that is 2 times the semi-major axis, which also happens to be the apocenter distance and the pericenter distance. So we can write 2 times the semi-major axis is equal to the apocenter plus the pericenter. So that gives us our full major axis in the ellipse. Now, if we then substitute this into, or we take that into account and put it back into the equation we just had, we actually can again remove out the pericenter distance, and we've got it in terms of the semi-major axis instead now. So now we've got the velocity in the apocenter, the distance of the apocenter, and the semi-major axis. Okay. So now if we again go back to our specific orbital energy equation and we substitute what we've kind of got into that, then what we can basically do is we can get this form here. And if we just rearrange that, this then gives us our Vis Viva equation at the bottom. So V squared is equal to GM, then you've got some brackets there, where it's 2R minus 1A. But we can simplify that a little bit further. So we can actually take the square root of that, and then that then gives us our Vis Viva equation. And what we need to know then to get the velocity of that object on its elliptical orbit is the distance between the two objects at that time, that point on its orbit, the semi-major axis A, and also the mass of the larger object, or because normally the second object is negligible in comparison. So we just need those 3 things and we can get the velocity of the smaller object on its elliptical orbit depending on where it is. So thank you for watching. If you enjoy the videos or find them helpful, then do consider becoming a member of the channel. There's extra videos in the member section, but it also helps support the channel. So thank you for watching.